Hello learners, and welcome to a video tutorial about the magnetic field off of a current carrying loop of wire with radius r. And we're going to be off center from this thing a certain distance x. And you can kind of visualize this with just a little tack. And we're going to figure out the magnetic field at the very tip of the point. Whoop, and our current is running around this outermost edge of the tack. So what I've done is I've kind of drawn this at an angle, I've tilted the tack inwards like this. And so our loop is kind of running in. So really, this section of wire is technically going into the board. This section of wire, the current is coming out of the board, and it's going around like this. So it's going in, across, out, and over. In, across, out, and over. Okay. And to figure out the magnetic field here at point P, we're going to be utilizing the Biot-Savant law. And so we've got mu naught I over 4 pi times the integral of dl cross r over, whoops, that is r cubed. But this is going to simplify down to r squared, and here's why. I'm going to change this dl cross r, and I'm going to change it to dl r sine theta. And that theta is the angle between dl and r. Now, I've got r and r cubed on bottom, so you can see that this just becomes dl sine theta over r squared. Now, let's talk about this angle between dl and r. First off, dl is just going to be a very thin section of wire. So in this section, my current is going into the page, or into the board here. So again, I've got this current carrying loop, but I've drawn it like this, but in actuality, it's really like this, and my loop is right here. And I'm investigating this really thin section, and the current is going like this, which means if I really think about what this actually is, the current is going in. So if I wanted to figure out the direction of magnetic field from this, well, first of all, I am a certain distance from that point. I'll call it r. Now, to figure out the direction of magnetic field, first you would grab the wire with your thumb pointed in the direction of the current. So my thumb is pointed in, and so this thing is creating a magnetic field that is clockwise. But when you are doing a cross product, the magnetic field is going to be perpendicular to what you are cross-producting. So I'm cross-producting dl and r. Well, dl, we said, is going into the page, into the board. And r is running like this. Well, the only way that I could have my magnetic field, be perpendicular to both of those is if I drew it like so. Now here I'm perpendicular to r, and I'm also perpendicular to dl. Here's why. dl is going into the page, and b is in the plane of the page. Think about your xy and z axis. Okay, so there's z, x, y. By definition, z, or dl, is perpendicular to the x and y axis. So b needs to be somewhere in the plane of the page in order to be perpendicular to dl. Now, it has to be perpendicular to r too, and it was going this way, so that means that at that point, b and r are perpendicular to each other like that. Now, this sine theta is the angle between r and dl. Well, r is also in the plane of the page, and dl is in that z-axis, that z-axis. So by definition, r and dl are perpendicular to each other, which means that sine of theta is just 1. So this leaves me with magnetic field being equal to mu naught I over 4 pi times the integral of dl over r squared. Now here's what's great about this. R is a constant. R is not different no matter which part of wire that I investigate. R is equidistant anywhere to the wire because point P is here in the center of the circle. So R is a constant, I can pull it out. Now R is dependent upon how far away point P is and the diameter of, or excuse me, the radius of my circle. But I could say that if you look at the triangle that I make here, r squared is equal to x squared plus the radius of the circle squared. So I could make that substitution in here. Now, this B that I've drawn is the magnetic field from this very small section of wire. Well, what if I did a very small section of wire on the exact opposite side? Well, again, this current is coming out towards us. So I would grab the wire, curl around, and here is R again. So the B field from that section must point like this. Now, both of those vectors are equal in magnitude, and if you look, their x components are going to cancel out. I'm going to get this no matter which section of wire that I investigate. If I did the front and the back, my magnetic field from this section of wire would be coming kind of out towards us, but from the back section it would be going away from us. So everywhere, how I've drawn it, the horizontal components are going to cancel. So that leaves me with the only net magnetic field being in the y direction here. So really what I want is By. Okay, so I want By for the entire wire. Okay, well, if I know the equation for B, the hypotenuse here, because again, I've got By going up and I've got Bx going across like this. Well, we need to figure out the y component of that vector there. Okay, well, because of the fact that B and R are perpendicular to each other, and By runs along this x, or this x distance here, I make an angle here that is equal to this angle here. Call it theta. So By would be B, and By is the adjacent to this angle, so it would be B cosine theta. Well, if you look, theta would be adjacent over hypotenuse. So this would be B times cosine of theta, which would be big R over R. But remember, R, I've got R squared here, so R is just the square root of x squared plus R squared. Okay, so I have By. Let's take this and let's get it in here. So I have By equals B, which is this right here, but remember R is a constant and it's equal to x squared plus R squared. So I can pull this out and that would give me mu naught I over 4 pi R squared, but again R squared is x squared plus big R squared. Okay, times the integral dl, and then times cosine theta, which was R over the square root of x squared plus R squared. Now looking at that, inside my integral, well, the radius of the loop is a constant, the distance out to where I'm measuring the magnetic field is constant, And then I've got the radius of the circle again. So all of this I can take out. So that gives me by is equal to mu naught I over 4 pi times this x squared plus r squared times r over the square root of x squared plus r squared. Well, the square root of x squared plus r squared is like x squared plus r squared taken to the 1/2. And if I'm adding, or if I'm multiplying these two, I'm just going to add their exponents. So that would be x squared plus r squared to the 3/2. And then still times r. Now, I've still got this integral of dl. Well, I've just got the integral of dl, and that's like 1 dl. Well, dl is, I want to integrate a small section of wire to the entire section of wire. Well, that would just be the length of the wire. And since I've got a circle, how handy is this? R over 4 pi, and then I've got x squared plus r squared to the 3/2 times, well, the integral of this is just going to be the total length of the circle, which is just 2 pi r. And I can make some pretty slick cancellations here, and I end up with all of my magnetic field up, which is my net magnetic field, being equal to mu naught I r squared over 2 times x squared plus r squared to the 3/2. Now, what would be the only thing different if instead of my loop and my point being up, what if I turned it like this? Well, now all of my vertical components will cancel, leaving me with only a magnetic field this way. Now, looking at this, x is the distance from the circle, or from that center point out. If I were actually inside the center of my loop, in other words, current is going around like this, and I'm right here, my magnetic field is not 0. X is 0, but my magnetic field would not be. So again, you can look and see, okay, what's the trend as I start in and then move further out or go back the other way, and you aren't going to get a 0 magnetic field for this loop. So there you have it, the Biot Savant for a circular loop and a point off center of that loop.